In the high rises of Tokyo, Osaka, and Yokohama, you're dominating the cityscapes that surround you. These towers give a powerful impression of being as immovable and steadfast as human-made structures can be, fixed to the backdrop of urban daily life in Japan, just as they are in any other developed city in the world. While they stand tall, the city moves around them. People and traffic bustle, and they stand still as the pieces that tie the hectic town together. If you've ever experienced an earthquake swaying the world around you, you might know what it's like to feel like your world has grown chaotic. The perspective and perception of the immovable object is simply an illusion. An object that cannot be moved cannot stay that high if the ground beneath it wants to shake it down to its core. In Japan, these skyscrapers have to move. Hey guys, welcome back to Trends in the World. Today we're going to take a look at how skyscrapers in Japan are built and how they withstand the minor earthquakes. These occur several times throughout Japan's lifetime. For these, any damage is unacceptable. Buildings must be designed so well that earthquakes can pass without leaving a scratch. Withstanding extreme earthquakes, these are rarer, but the bar was set by the Great Kanto earthquake of 1923. With a magnitude of 7.9, it devastated Yokohama and Tokyo, killing more than 140,000 people. For extreme earthquakes, resilience standards allow for some damage, as long as it does not cause human casualties. Instead of focusing on preserving buildings, the priority is protecting lives. In places frequently hit by earthquakes, this is the minimum requirement: protect people. How do they do it? To withstand incredible forces, buildings must absorb as much seismic energy as possible to prevent collapse. The process that makes this possible is called seismic isolation. Buildings or structures are set on supports with shock absorption, sometimes as simple as rubber blocks that are about 12 to 20 inches thick. These rubber pads resist the motions of an earthquake and take pressure off the buildings. They are placed wherever columns extend down to the foundation. Motion dampers throughout the height of the building also improve resilience. If placed at certain levels, like every other floor, they reduce overall motion during an earthquake and prevent widespread structural damage. These dampers resemble bicycle pumps, but are filled with liquid instead of air. When compressed, they push against the fluid, which slightly moves and reduces vibrations. Often, designers of spectacular skyscrapers are reluctant to make compromises to meet seismic standards. But complex devices and tension-resistant materials are not the only way to make buildings earthquake-resistant. Overall design plays a major role. For example, the more regular a building's design, the better. Keeping floors at a standard height and ensuring an even grid for columns help improve performance during earthquakes. However, this often clashes with architects' more ambitious design visions. Using mesh structures is another way to prevent a building's supports from buckling. If one part buckles, nearby supports help distribute the energy evenly, reducing the risk of collapse. A Japanese textile firm took a different approach by using carbon fiber rope. They developed a high-tensile twine from a carbon fiber composite to reinforce their showroom and laboratory in Nomi. Working with Japanese architects Kengo Kuma and Associates, they used 1,031 rods attached to the roof and 2,778 rods inside to stabilize the structure. This may be the first time carbon fiber has been used in this way, but it could be applied to flexible structures like wooden buildings that sway horizontally. The future of earthquake proofing. Creating truly earthquake-proof buildings is not a static process. Researchers estimate how earthquakes might impact structures by continually monitoring seismic activity. In 2021, 2 major earthquakes, both above magnitude 7.0, struck Japan, one in Fukushima, 7.1, and one in Miyagi, 7.0. These events are becoming more frequent, making it harder for seismologists to predict them. The solution lies in continuously testing known stabilization technologies and experimenting with creative designs. Some recent designs use polyhedral mesh structures that resist buckling entirely, such as those designed by architect Sou Fujimoto. Looking at Japan's past may also provide insights into the future. The country has endured 61 earthquakes above magnitude 7.0 since the Horyuji Temple was built in 607 AD. So how has this 122-foot-tall wooden pagoda survived for centuries? Japan adapted the pagoda design to its seismic conditions through three key elements: wide and heavy eaves, disconnected floors, shock-absorbing shinbashira, central pillar. A modern example blending ancient and futuristic engineering is Tokyo Skytree, the world's second tallest building after the Burj Khalifa. It incorporates elements of traditional Japanese pagodas, including a central pillar attached to seismic dampers. The shinbashira technology prevents excessive floor movement. While acting as a load-bearing column, it does not support the building's weight. Traditionally, this was a large pine trunk suspended from the roof down a central shaft. In some cases, it lightly rests on the ground, while in others it hangs freely. This pendulum effect absorbs shocks and swaying caused by earthquakes. Even today, mass dampers based on this concept are used worldwide. Taipei 101 has a 730-ton steel pendulum on the 92nd floor, preventing excessive sway in high winds. New York's Citicorp Center has a 500-ton concrete block that stabilizes the building against hurricanes. The future of structural safety innovations continue to push engineering and design to new levels, making structures safer. The commitment of engineers and architects to protect human life remains a top priority. We will have to see how they continue to integrate ancient knowledge with modern technology to advance earthquake-resistant designs. For now, we can admire the incredible structures they have created. Have you ever experienced an earthquake in a skyscraper? Subscribe and turn on post notifications for more content like this. That's it for today. Thanks for watching. See you in the next video. Until then, stay curious, stay informed.